STAAD design parameters LY, LZ, DJ1 and DJ2. If you have spent enough time in structural analysis, you have probably noticed something interesting. People assume that understanding of LY, LZ or DJ1, DJ2 becomes clearer automatically as you gain experience. As if one fine day after years of practice, the correct definition of these parameters will suddenly reveal itself. We all believe that. We thought experience alone would teach us how members truly behave under load, how bracing patterns influence effective lengths, and how LY or LZ should be assigned just by looking at the structure. When we were juniors, our seniors would glance at a plan or an elevation of a structure and confidently say that LY for this member should be this much and LZ for this member should be this much. And we were amazed. It felt like magic, structural wizardry. Today we are seniors and we do the same thing. We glance at model, declare LY or LZ, and juniors look at us with the same admiration we once had for our mentors. Can you correlate this? Yes, definitely. But here is the twist. Even after years of experience, the definition of these parameters still varies from person to person. Two engineers, same structure, different LY or LZ. Why does this happen? It shouldn't happen, because structural behavior doesn't change based on who is analyzing it. A member's bending, buckling or bracing behavior is not personal. It's rational, predictable and governed by mechanics, not opinion. So how do we define LY and LZ correctly? The rational way: stop relying on intuition alone. Stop relying on this looks right or this looks wrong. My senior used to do it this way, that's why I'm doing this. Instead, look at the bending moment diagram due to the member's own self-weight. I'll show you. Suppose this is an elevation of a structure which consists of some bracings at a brace bay, you can say, and there are some partial bracings also. So now I have to define LZ for this elevation or these horizontal beams. What I will do, I will apply the self-weight of these all structural members in vertical Y direction, downward direction, and examine what is happening with the bending moment diagram. Okay, so this is the applied load and bending moment diagram. So what is happening with the self-weight of these members? We can find that certain kinks are formed. There is a change of the direction of the bending moment is happening at the base point locations here. So what does it mean? These points are actually acting as a support to the whole beam here. So what does it mean also? That means my beam is getting broke at these points. So LZ will be this portion and this portion and this portion. Similarly for this also, this bracing is breaking my beam in these two parts. If I zoom in and check this point, what is happening at this point, we can see the next figure with enlarged bending moment diagram. Here we can see there is no change in the bending moment diagram, even though I have one stub here which is connecting these two beams, which is not going to act as a break point or breaking element for this member. So my LZ will be from here to here and from here to here. And what is happening at the brace point locations? I told you at this point will act as a support for this member. So LZ will be up to here and another portion will be to here. Similarly for this bracing. In this way, we can define LZ by examining the bending moment pattern. Similarly for the plan, if I want, this is the X direction of STAAD and this is Z direction. If I want to define the LY for the beams parallel to X, I will apply the self-weight in this direction and examine the bending moment diagram. So this is the bending moment diagram, and very well I can see that this point is acting as a support for this beam. So LY will be half or whatever the length available here from this end to the break point. Similarly, what is happening here? This portion is also getting broke. This portion is also getting broke because of the effect of this bracing hole. Now, but the whole bracing effect is not getting transferred up to here. Maybe because of the brace bay and everything, here I cannot see the break point. So what is happening? Because of this additional bracing, this beam is getting kink at this location. That means this location. So Ly will be up to here, and Ly will be up to here. Blindly, we cannot follow that this bracing pattern is dividing my all the beams in half or based on this bracing pattern. Not. Something is influencing, that is this bracing pattern is also getting influence on these beams. Similarly, if I want to define Ly for the beams which are parallel to x direction, what is happening if I apply the self weight in this direction and check for the bending moment pattern? This is the bending moment pattern. Here I can see the support or the kink in the bending moment diagram. So these beams are broke in these pieces. So application of the self weight in the respective direction will help me to analyze the bending moment diagram and define where my beam is breaking just because of the bending moment pattern. The very rational method can be used in the complex bracing patterns to define the Ly or Lz. Once you understand this rational approach, you will never again depend on guesswork or someone's visual judgment. Hope I brought the clarity, right? After you grasp this logic, don't stop here. Automate it. Use OpenSTAAD with simple Excel VBA to read bending moments and shear force and generate Ly Lz automatically. Excel is already your daily companion, and I know how fond you are of it. So use it to build your own utility. And yes, if you want a ready-to-use tool that generates design parameters based on the exact rational principle which we have discussed right now, it's available to download it and you can use it. Structural engineering becomes powerful when intuition and automation work together. So keep learning, keep coding, and keep refining your workflow. Your future self will thank you.